Multimodal learning, MML, has gained significant attention for its ability to compensate for single-modality limitations by leveraging comprehensive complementary information within multimodal data. However, traditional MML methods suffer from the modality competition issue, where a dominant modality hinders the learning of weaker modalities, limiting their full potential. To address this challenge, this paper introduces detached and interactive multimodal learning, DI-MML, a novel detached MML framework designed to learn complementary information across modalities while avoiding modality competition. The DI-MML framework employs a detached learning process, where each modality encoder is trained separately with isolated learning objectives, eliminating modality competition. A shared classifier defines a common feature space, facilitating cross-modal interaction. The dimension-decoupled unidirectional contrastive (DUC) loss enables modality-level knowledge transfer, while a certainty-aware logit weighting strategy effectively leverages complementary information at the instance level during inference. The proposed method differs from traditional MML approaches, which use a joint training framework and a uniform learning objective, leading to modality competition. By assigning each modality with isolated learning objectives, DI-MML ensures that all modalities contribute equally, avoiding the dominance of a single modality. Extensive experiments on audio-visual, flow image, and front-rear view datasets demonstrate the superior performance of the proposed method, achieving consistent improvement in both multi- and unimodal accuracy. The DI-MML framework consists of two key components: a shared classifier to regulate a shared feature space and a DUC loss to enable sufficient cross-modal interactions. The DUC loss encourages the transfer of modality-level complementary knowledge, and the certainty-aware logit weighting strategy utilizes instance-level complementarities during inference. The proposed method is the first to completely avoid modality competition while ensuring sufficient cross-modal interactions in MML, making it a significant contribution to the field. The Detached and Interactive Multimodal Learning (DI-MML) framework addresses the modality competition issue in multimodal learning by training multimodal encoders separately and facilitating feature space alignment and cross-modal interaction through a shared classifier and dimension-decoupled unidirectional contrastive loss (DUC). During inference, logit weighting is utilized to separate effective and ineffective dimensions of each modality, transferring complementary knowledge between modalities. Experimental results on 4 datasets demonstrate the effectiveness of DI-MML, outperforming state-of-the-art methods. An ablation study shows that each component is essential for achieving optimal performance. The framework's dimension separation scheme is evaluated, demonstrating that effective dimensions are more informative. Additionally, the robustness of DI-MML to hyperparameters and batch size is investigated, showing marginal effects. Overall, DI-MML presents a novel and effective multimodal learning framework with potential for further research and applications. Here is a combined summary of the content from pages 912. The paper introduces detached and interactive multimodal learning, a novel approach that analyzes interactions between modalities to identify the most informative dimensions for each modality, thereby enhancing multimodal task performance. The authors evaluate this approach using the CREMA-D dataset, which contains emotional multimodal actors' videos, and demonstrate its superiority in terms of accuracy and robustness compared to other multimodal learning models. They further explore cross-modal interactions and identify specific semantics in each dimension, finding that certain dimensions are more informative than others, and focusing on these dimensions can improve the performance of the multimodal learning model. The paper also discusses the limitations of the approach and suggests future work, including investigating other types of cross-modal interactions and focusing on multimodal tasks like detection or generation instead of classification. Identifying specific semantics in each dimension may be helpful in evaluating informative dimensions. The authors utilize several datasets for emotion recognition, audio-visual event localization, action recognition, and 3D object classification, including CREMAD, Avenue, UCF 101, ModelNet 40, and CMUMOSI. These datasets are described in detail, providing information on the types of data, number of samples, and their use in the experiments. The proposed method is compared with 8 multimodal baselines, each briefly described, highlighting its key features and differences from the proposed method. The training scheme for the proposed method involves unimodal training for warm-up epochs, followed by the application of the shared classifier and duck loss for the remaining encoder training epochs, with the fusion module trained separately after the encoders are fixed. Additional results are provided on the CMUMOSI dataset, where the proposed method outperforms a new baseline, I2MCL. The effectiveness of the proposed method is also verified using different model structures, such as ResNet 18 and PointNet for image and point cloud data of model Net 40 for classification.